Hello, everyone. My name is Hannah Farabee. I am a graduate student at Michigan State University here in East Lansing, Michigan. I will be the one conducting the lectures over on our research project to identify fish ponds using satellite imagery in southern Bangladesh. So today is the first recording of these lectures, and I'll be giving an introduction to remote sensing as a field, and we'll just be going over some really broad topics. I am going in with this assuming that none of the audience knows anything about this, so I apologize if some of you do have a background, but this will just be, a nice review. So to start, what is remote sensing? So remote sensing is the process of collecting data without directly measuring an object. So we're not holding a ruler to it. We're not, seeing necessarily like what physical characteristics it has. We're measuring, what instead we're doing is we're measuring different reflected or emitted energy from that object. And so what this entails is that we use a sensor to collect light that has light or other energy sources that have been emitted from an object or are reflected from an object. So this is similar to how our eyes work. Our eyes work by collecting light introduced either by the sun or fire or lights, and that energy bounces off different objects and surfaces, and then goes into our eyes, and that's how we're able to see the world around us. And so with this, different wavelengths of electromagnetic energy can tell us different things about the target. So a super easy example of this is, so red light has a different wavelength than blue light. And so when we look at something that reflects blue, we know it's blue, whereas something that reflects red, we know it's red, and those things can tell us different things about a target, whether something is hot or maybe something cold, like when we go to a faucet. So for conducting remote sensing, there are a few different platforms that we can use. And so a platform is just like, what are we putting the sensor on? And so the most common and most probably thought of platform for remote sensing sensors are satellites. And so this is a little image of a satellite collecting data from the planet. Another common platform that you might think of are drones. So these are unmanned, aerial devices, I think is the proper term. But so drones, these are typically used at a small scale. And so like here in the US, we use drones a lot to monitor different agricultural crops to see, where, what areas maybe need more water, what areas might have diseases impacting them, things like that. So if you have a small-scale project, a drone is really useful and can be an inexpensive way of doing some monitoring. And then lastly, the third common platform for remote sensing are planes. Sometimes these can also be helicopters. But before satellites, we used planes to collect most of our aerial images. And so if you look back far enough at some historical images, you will see that they were collected by planes and not satellites. And this is still done for certain projects today. So here is a diagram of remote sensing in action. So up top, we have a helicopter. So we've got an aerial platform, whether that we could easily replace that with a drone or a plane or a satellite. And then on that on that helicopter, right at the bottom, there's a black rectangle. And so this diagram is pointing to it, saying that is our remote sensing instrument. So when I say a sensor, that's where our sensor is. And we want it on the bottom of our platform because we want it pointing down, because for large-scale remote sensing, our target is the surface of the Earth. And so here you can see that the sensor is currently collecting data about these trees. And so this is the collection of information about an object, for example, these trees, without being in direct physical contact with that object. So instead, what the sensor is doing is collecting different reflected energy or emitted energy from these trees. So typically when we're talking about remote sensing, you will also hear there's something called GIS. Some of you may be familiar with this in your work, but GIS stands for Geographic Information System. So GIS is a technical discipline that uses computer-based geospatial data to map and model geographic information. So GIS is composed of, very specifically, it's composed of computer hardware, software, geospatial data, and then a person then to operate the system. So when we say geospatial data, we're talking about data that has a geographic location associated with it. So that is when someone says data in a conversation where you're also saying geospatial data, you know that whatever they're talking about may not have a geographic location associated with it, and so that's why sometimes it's really important to specify that, no, I'm working with geospatial data, or I am looking for geospatial data. So for an example of this could be a satellite photo. So whereas we could have, a photo taken with our camera, this satellite photo, like each different part of the photo corresponds to a very specific location, and that information is embedded in that image. So some examples of different GIS softwares. So there's quite a few out there. I chose these three because they are typically the most common, I would say. And so these would be like Esri ArcGIS software, which some of you may be familiar with or have heard of it. And then there's QGIS, which is a nice open access software. And then there's Google Earth Engine, which I wouldn't say is a software, but it's a platform online. It's an online platform that we can use. So it doesn't necessarily fit in the same category with Esri and QGIS, but it does a good amount of the same things. So we'll first talk about Esri ArcGIS. So Esri ArcGIS software can be used for really a wide range of tools. More generally, it's used for data manipulation and spatial analysis, but really that's just like scratching the surface. There's a whole depth to this software, and because it's so comprehensive, this software is very expensive. They do, I know, have a free online platform, but it's a very, very simplified version of what their software is, but it is expensive. So because of this, I believe QGIS came to be. So it's a free and open access software. It's very similar to ArcGIS, except that since it's open access, it is pretty much like community run. So different people online can make different libraries for it and different tools for it. Also, because of this, you may find less documentation on how to use the platform. But if you're very interested in trying to learn a GIS platform, I highly recommend QGIS. That's not what I'm going to be teaching within the next few lectures, But if you're interested in this topic, you feel free to come to, I know I'm going to be hosting some office hours, feel free to come and we can talk more about it. But it's a really interesting platform if you aren't at a university that may have ArcGIS or not at a company that may also have ArcGIS licenses. So here is kind of like what the ArcGIS Pro platform looks like. So it's a software with many tools. Here's just, this is a parcel map. So I just want to kind of show you what this looked like so you had like a clear idea in your mind. And then this is QGIS. So it's a bit of a more simplified layout. These are, I believe, street. This is a street map, but they do very similar things. But with QGIS, it's like a lot more self-taught than ArcGIS. So, but they do look very similar. And then lastly, we have Google Earth Engine. So this is what I will be teaching for the remainder of this course, because that is what we used in our research. And so Google Earth Engine, I just want to specify right at the beginning, this is different from Google Earth. Google Earth is a software that you download from Google and is on your computer. And you can't really do any sort of manipulation with satellite images with it. Google Earth Engine is a repository of numerous satellite data sets. So originally, they only really had the freely available data sets, but more recently, they've started working with some private satellite companies and are being able to obtain really, really nice satellite images that we can then use for free that wouldn't normally be free. So if you're interested in like learning more about that, I know Google Earth Engine, when you sign up, they have a blog that will keep you updated on everything. And so then with Google Earth Engine, you can manipulate data. So I apologize. I know earlier I said that data is different from geospatial data, but really it is. But I should have also specified that pretty much from now on, when I say data in these courses, I mean geospatial data. So you can manipulate geospatial data. You can export data or images, and it's free to use, which is very nice. But there are certain data limits and like computational limits with Google Earth Engine. So Google Earth Engine looks a bit different than the other two, and that's because it's not a software, it is an online platform. And really everything that you do within Google Earth Engine is coded. So they use JavaScript. JavaScript can be a bit difficult to learn, and so, but I will be going through that in some of our later lectures. But Google Earth Engine does provide very, very thorough documentation. So, and I can show you later how to access it. But primarily, there is an area where you would type in all your code, an area to access your files. The console where you would print things out, and then the map to see different places where you added visual data. So there are two formats for geospatial data, vector and raster. Raster data is gridded information made up of pixels, and pixels are the smallest unit of measurement in a raster. So you may be familiar, you've maybe already heard the word pixel when talking about particularly like screens. And so pixels are they are the smallest unit of measurement, and they are, each of them holds a certain value. So here at the bottom of the slide, I have an example of raster data. And so each of these little squares represents a pixel, and each of the values ranges from 1 to 4. And so, for example, this could be, just a small subsect of a much larger, raster that holds a lot more data. And the most common example of a raster data are images. So pictures that you would take on your phone, that is an example of raster data. So the second one is vector data. So these are not made up of pixels, but instead they are shapes. So this could be a line, a point, or a polygon. These do not hold reflectance values. Typically, they're just there to not in the same way that a raster data would. But on a map, you would just maybe put like a circle to highlight like your area of interest, or you might put a point down if you're looking at where are different types of trees in a forest, and you can put a point down like, oh, there are maple trees, things like that. So it's more of it's shape data rather than image or gridded information data. So it's really important when talking about remote sensing to understand all the different types of wavelengths that we can use. So as I said earlier, different wavelengths of the electromagnetic spectrum, or EM, are used in different ways and require different sensors. So the main three categories that I would say come up the most often, generally, of EM spectrum are visible light. So I have it highlighted here in green. So visible light is what we see with our eyes, and all of the colors are some mixture of blue, green, and red. This does vary from, you may be more so familiar with in an art class, the primary colors are blue, yellow, and red. But when we're talking about light and even screens, it's red, green, blue, which you probably all have heard of RGB. And so RGB is red, green, blue. And the red, green, blue make up all of the colors that we see. They are, the wavelengths range from 400 to 700 nanometers. So, and you can see in this diagram that it's a very, very small section of our entire spectrum. So the next up is infrared, and infrared makes up a much larger chunk of the electromagnetic spectrum. So infrared consists of many different types of infrared. So there's near infrared, which is typically denoted as NIR. There's shortwave infrared, thermal infrared, and then down at the bottom you can see that there's also photo infrared, which is part of the near infrared spectrum. And so all these things tell us, all these wavelengths tell us different characteristics about about an object. And so, for example, I know I have said, when it comes to remote sensing, we're looking at either energy reflected or energy emitted from a target. And so an example of energy emitted from a target would be thermal infrared. So, or you can think of it as heat, or the absence of heat. So when we're looking at thermal infrared, we're looking at what is the temperature energy being released from the object. Some of you may be familiar with heat maps. That is an example of thermal infrared. And then lastly, we have radar. Radar or microwave. These wavelengths are the largest wavelengths that we use. And I believe some of them go even after microwave and radar, there's radio waves, and those those wavelengths are meters long. They're very, very large. So then another way you may hear different wavelengths discussed is optical and non-optical. So optical wavelengths are ultraviolet, visible, and infrared. So they can be manipulated in some way during their path. Whereas non-optical wavelengths, these have many, many different uses, but they behave differently than optical wavelengths do. So here is another example of the electromagnetic spectrum. So as you can see, with gamma ray, X-ray, ultraviolet, so this spectrum goes way further out than what the last one did. But so ultraviolet would have the shortest wavelengths, highest frequency, higher energy, whereas microwave and radio have the longer wavelengths, lower frequency, lower energy. So when we're talking about sensors, we also discuss how they work. And so this can be broken up into two main categories, passive and active sensors. So a passive sensor measures electromagnetic energy emitted or reflected from the target. So this is the top little diagram here. These would be only optical sensors are passive typically, and they can only be used in sunny, cloudless weather. And that is because they rely on the source to either make or reflect its own energy. So here at the top, we see that our energy source is coming from the sun, and so the sunlight hits the orange cat, and then some of it is reflected to our sensor on the satellite. Whereas an active sensor emits its own electromagnetic energy that is then reflected or absorbed by a target, and then the sensor captures what is reflected. So these are all radar sensors, and a huge benefit of these is that they can be used in all weather types. And so you can see in the bottom diagram that our sun is blocked by a cloud, and so this satellite, it's an active satellite, so it is producing its own electromagnetic energy. That is, some of it is then reflected by the orange cat and captured then by the sensor on the satellite. So this leads us all into pretty much the main type of data that we use, which are images. So, but what is an image? An image is a representation of reality, whether that's reality that we see or reality that we can't see, because we can't see certain wavelengths with our eyes. So satellites capture and store these electromagnetic waves from features on Earth, very similar to how a camera captures an image of a landscape that you're looking at. And then these images are composed of those small square pixels, and each pixel contains a certain value of reflected energy, reflected or emitted energy. So now I'm going to be getting into types of images. So first off, we have panchromatic images. These are black and white images where black represents high absorbance. So high absorbance is just low reflectance, which means that whatever the target is, it is absorbing most of that wavelength of energy and is not reflecting any. And then white represents high reflectance, and another way you can think about that is low absorbance. And so each pixel in panchromatic represents a measure of reflectance of that specific wavelength. And so this example on top shows that, I'll start from the right side of it. So we have this grayscale where the value way up high is white, and that corresponds to a value of 255. 255 is a pretty standard, so 0 to 255 is the standard range of all values. So if something is pure red, it would be 255 red. If something's pure blue, it would be 255 blue. So 255 is pure white, which means full reflectance. And then once you get into the gray, it's about halfway, so 127, and then a value of 0 would be pure black or no reflectance whatsoever. And so you can see here on the roster, then on the left side of this diagram, we have a wide range of different shades of gray. We have some pure white and some pure black. And then next to that is the numerical values for all of those pixels. So I hope that this kind of connects that like numerical pixel value aspect to then how we visualize those values. So then below, I'm sure you're all familiar with what black and white photos look like, but it's this works very similarly. So we have some areas that are very, very dark, which means that those are areas of high absorbance. Then we have some areas in this image that are very, very white or very close to white, and so those are areas of really high reflectance. So then next we have red, green, blue images, or RGB images. These are also called true color images. Here I have an image of Ann Arbor, Michigan. This is where University of Michigan plays football. But as you can see, these all appear in the colors that most of us see them in. If you are colorblind, you see colors differently. But this is, the trees are green, the roads are gray, things like that. So these are how we visualize the world, and that's why it's referred to as true color. And now we'll get into the opposite of this. So we also have these images called false color images, and these are the result of answering the question, how do we visualize wavelengths that we can't see? So if you remember on that spectrum, the visible wavelengths were only a very, very small section of the entire spectrum that we can use. So these false color images assign a wavelength to a visible light color of red, green, or blue. And so this chart that I've included is relative reflectance for green vegetation. And so on the y-axis, we have these letters, and those correspond to low, medium, high, and very high reflectance. And then on the x-axis, we have different wavelength ranges. And so I've gone ahead and labeled those so that they're a bit easier to understand. So something interesting about vegetation is that we see, when we look at vegetation, we see green. And that is because out of the visible wavelengths, green has the highest reflectance out of the three. So, and that is why most plants, I don't want to generalize all of them, but most plants appear green to us. But if we were able to see near infrared, the plants would appear that way to us because plants have a much higher near infrared, or NIR, and so that's those really tall columns. So plants have a very high near infrared reflectance, more so even than its green reflectance. And so near infrared can be extremely helpful in identifying where vegetation is. But we can't see near infrared. And so what we do is we assign a wavelength to a certain channel. And so when I say channel, I mean we have three channels. We have blue, green, and red. Those are set. But those may not be representing that actual color. So blue may not always actually be representing something blue. So when so a common visualization for green vegetation is to assign green reflectance to the blue channel, red reflectance to the green channel, and near infrared to the red channel. So this can get confusing sometimes. So I think when you're working with a false color image, it can be extremely important to potentially, put down what each channel represents. So, maybe write it down next to you or have it in some place important so you can always remind yourself, because it can get confusing sometimes. So here is an example of a false color image. So here this represents, we're trying to visualize where green vegetation is. So here you can see a significant amount of red. And so every place that you see red is very, very high near infrared. And so reflectance. And so we can pretty much say that everywhere that's really, really high red in value, that's where there is vegetation. And so then everywhere that we see green in this image, we know that there is some sort of red reflectance. And then wherever we see blue, that's where there would be a green reflectance. So even as I was describing it, I even had to, remind myself, red is high vegetation, because that's where high near infrared reflectance, things like that. So it can be really important just to keep reminding yourself what each is, because these are false color they're named that for a reason, because these aren't how we see colors in our day-to-day life. So they can be tricky. They can be very tricky. Okay, so now back to satellite sensors. There are 3 different main ways that we characterize sensors, and we can compare sensors that maybe collect the same or similar information. So the first characteristic is its spectral resolution. So spectral resolution describes what wavelength bands are being measured by this sensor. Is the sensor multispectral, meaning does it capture many wavelengths? Is it hyperspectral, meaning does it capture a lot, a significant amount of wavelengths? Or is it panchromatic, meaning it's only measuring one? Or maybe it's microwave or radar. So here we have 2 different graphs showing the different bands of 2 different satellites. So 2 very, very common satellites that have kind of like a long history are Landsat 8 and MODIS. And so when I say a band is a range of wavelengths in which we will characterize something. So for example, we can say for this top one, band 7 here is in between 11 and 11.5 micrometers. So any reflectance that we get between those things will be assigned the band 7 label. So it's just a way to characterize ranges of reflectance, rather than we can only have 11 and we can only have 11.5, but instead we can have between 11 and 11.5. So you can see how different the Landsat and the MODIS bands are from each other, and how many they may have. So this is a way to characterize different sensors. So the second characteristic is spatial resolution. So this refers to what ground size does the pixel correspond to. So a common one that you might see is 1 pixel equals 10 meters on the ground. So an example of this, on the left of this image, we have 30-meter spatial resolution of a city. And you can see that we use the phrase, it's pixelated. And when we say pixelated, it means that you can tell that there's pixels in it. The image isn't very clear. We can obtain some good information from this, but if we wanted very, very detailed observations, 30-meter spatial resolution would most likely not be adequate enough. And then here on the right, we have a 1 meter spatial resolution aerial photograph. So a benefit of using, say, planes or drones is that a lot of times we can get much better spatial resolution than we can with a satellite. So here you can see the clear difference. So each pixel then on this image corresponds to 1 meter. So we get much clearer images. We can tell what we're looking at. We can tell that we're looking at a city. Whereas with the 30-meter spatial resolution, Maybe if we zoomed out, we could tell what we were looking at a bit more. But the 1 meter spatial resolution is definitely better. Something to remind yourself, or that's important, when you're talking about spatial resolution, you might hear someone refer to as a spatial resolution that's high or low. And so this may be a little bit confusing, but when we refer to a spatial resolution that is high, so a high spatial resolution, we are referring to one that has a very small ground distance equivalent. So this aerial photograph would have a higher spatial resolution than this 30-meter satellite image. And then our last and third sensor characteristic is the temporal resolution. So how often are images collected? So this is also kind of described as like how, what is the time, what is the revisit time? So here on this map, I have a red square in an area of China. And so this satellite is moving along this path, and we're capturing an image in this square of China, and then the satellite is moving on. So temporal resolution describes the time between images taken at the same location. So how long does it take this satellite to return to the same square and take that same image in China? So here we on the right side of the screen we have an example timeline for remote sensor data acquisition. So the day of the first image was June 1st, 1999, and then 16 days later, the satellite returns to the same location to take another image on June 16th, 1999. And it goes on another 16 days, so on and so forth. And so we would say here that the temporal resolution is 16 days. So then, what's the importance of this? Or so what? Why do we even need to know this? So remote sensing can be applied to a lot of different situations, and the remote sensing research area is, it's improving and bettering itself every single year. We're coming out with new technologies. We're coming out with new research methods. It's a very, very exciting field. But remote sensing can be used for a lot of very important research and monitoring applications. So one of the most popular is land monitoring. So we can see how different land use changes over time. And I have an example of this, I believe, in our next lecture. We can also use satellite images to identify water, and we can also, within that, we can identify the quality of water and the quantity of water that is there, which is very interesting. And then we can also do monitoring of agriculture, as I believe I mentioned a little bit earlier. This really interesting map here is an example of weather monitoring. So you might be familiar with this if you check your weather app often and you want to look at the radar. So this shows where different storms are in the United States and how they're moving and their intensity. Another example of an application for remote sensing is national security. So I think all of us are a bit familiar that different militaries do satellite image reconnaissance, and so it can be used for things like that. And then there's also just certain economic applications of all of these. So most of this research, impacts, how are our crops growing? Can we find water? How are people moving? Can we see differences in urban land versus agricultural, rural land? Things like that. So that is the end of the main part of this lecture, and now I'm going to kind of walk you through setting up a Google Earth Engine account. And so this is important to try to do before the next lecture, or just do it right now as I'm talking you through it. But this is important because there is a wait time between when you apply for an application and when you get approved. I believe sometimes it's as little as 20 minutes, but I know some of my colleagues, I believe, have waited 1 or 2 days before hearing back from Google. So to start, you're going to go to this website. So you're going to go to earthengine.google.com. Feel free to pause this video and go there now. So then once you're at this website, this is the screen that you will see. So this is the Google Earth Engine main website, but we'll come back here next lecture. But what I need you to do right now is click this sign up button in the upper right hand corner. This sign up button will lead you to a Google sign in screen. So if you have a Gmail account, I would recommend using that, or you can also use an institutional email if Google will accept it. So if you have a government email or a university email, Google may accept that if your government or your university has a partnership with Gmail potentially already. Personally, I do use my Michigan State email address because Michigan State does have access with Google. So I just signed up with my MSU email because that was easiest for me, but you can use a personal Gmail. If you don't have one, just click the Create Account button and create your own Gmail. So then once you've signed in with Google, you're going to see this form. And so it'll say what email you have, and then you'll just put your full name, your affiliation or institution, your institution type, your country, things like that. Google Earth Engine does not allow private companies to use Earth Engine for profit. So you really have to specify if you're working for a government or if you're working for a research institution and not, for example, like a private engineering firm. And so here I have highlighted with the red arrow, this is a very important survey question. So what would you like to accomplish with Earth Engine? So here I'd like you to put something along the lines of, I'm interested in learning about remote sensing platforms or data sets, or like I want to conduct research of certain remote sensing topics in my country. I want to learn more about certain aspects of my country, something like that. So you're just making sure that you're saying, I'm not planning on using this for private enterprise. So because Google does not allow that, and if you say something along those lines that you want to use it for company profit, you will most likely be rejected. And then just agree to the terms of use. And most of you are probably not interested in commercial use of Earth Engine, so I would not select that. And then once you're done, just hit submit. And then just wait for an email from Google that will confirm your account. Please check your spam folder of your email. It may go there. But feel free to contact me if you do have issues. I know I will be having some office hours. So you can come and we can try to figure it out. But please just use a Gmail. Try not to do not say that you're using this for private company gain. So thank you for watching this video, and you'll hear from me in the next lecture.